It has been a pleasure to be here. So I'm a PhD student at IAC in Canary Islands, and I'm going to present the results that I found, or some interesting results that I found during my thesis. So to start with a brief introduction, as you all already know, in Orlando CDM cosmology, galaxies grow and evolve within dark matter halos. To understand how galaxies form, it's not only important to understand the complex baryonic processes occurring at the centers of these halos, but also how dark matter halos assemble. And the message I want you to take home today is that it's not only important to understand these two components, but it's also important to understand the interplay between the two. So how the baryonic cycle of galaxies is coupled to halo assembly. And a common way to study how galaxies and halos are connected is through the stellar to halo mass relation. So this relation is well known and has been broadly studied by different methods and techniques. And a lot of different techniques agree on their prediction of the mean relation. But what I want to focus here today, it's on its scatter. So here I'm showing again, this is stellar mass as a function of halo mass. And what's interesting is that there is scatter in this relation. So at fixed halo mass, there are halos that have been more efficient at forming stars than others. And there's quite a lot of tension in the field when we look how this scatter is connected to different present-day galaxy properties. So this has been studied by a variety of groups and techniques. And the idea is that while some works find that galaxies at fixed halo mass, when they become more massive, they also tend to have older or redder or tend to be passive. Others find that they tend to be younger, bluer, or star forming. And one of the main problems for that, or why is this an open question in the field and why it's highly debated, is that measuring halo properties is still a current challenge for observational astronomy. And not only that, but like these different works employ a variety of different techniques to obtain halo mass. For example, weak lensing, satellite kinematics, abundance matching, group and cluster catalogs, and all these methods have their own caveats and limitations. And in the case of theoretical models or semi-analytical models or hydro simulations, they also, how they implement their baryonic physics processes in their subgrid models also affect how halo assembly is coupled to the baryonic cycle. So, and as this is more about technicality, but I also want to say that it's also important to know when we compare different works, if we are studying the stellar mass as a function of halo mass, so basically studying the scatter as fixed halo mass, is different than if we studied it at the scatter as fixed stellar mass, given that when a lot of these works divide the galaxies into two different populations, for example, blue or red, and at the same time, they are winning into the x-axis of this relation. So if you actually change or invert the axis, you might get misleading interpretations. So that's a word of caution. So that in our first work, we use SDSS galaxies, and we compute the stellar to halo mass relation, so stellar mass as a function of halo mass, and these halo masses come from group and cluster catalogs, and we color code this relation with galaxy ages and metallicities. And we found that at fixed halo mass, this scatter correlates with stellar population properties. And this also that we also look at the star formation histories of the galaxies, also find that as galaxies, when they become more massive, they also tend to form earlier and over shorter timescales. And this is also something that was in agreement with the work of Greco Yosun and Kevin Bundy. Also, they studied manga galaxies, also using group and cluster catalogs. And for example, when they look at the age, they also find that their galaxies tend to be more massive at fixed halo mass. And this is all great, but again, these halo masses come from group and cluster catalogs, as I was saying. These are based on abundance matching measurements that are quite indirect. So in this work, what we wanted to ask ourselves is if there are alternative and more direct observational way of studying the connection between galaxies and halos. And for that, we use the CALIFA survey. So CALIFA is a diameter selected survey that selected galaxies from SDSS. and whose aim was to provide a spatially resolved view of the local universe. And what is special about CALIFA is that its spatial coverage that is quite large, and we are using a subsample of CALIFA galaxies that were observed with a high-resolution configuration. This high-resolution configuration allowed to derive high-quality stellar kinematics, which at the same time allow us to perform detailed dynamical modeling. So this is GEAN's axisymmetric dynamical modeling, JAM. So basically, by fitting the stellar kinematics, assuming a dark matter potential with a fixed concentration, we are able to derive the total mass of the galaxies enclosed within a given aperture. And in this case, it's 3 effective radii. So basically, we have a dynamical tracer of total mass that extends to a quite large extent, which is 3 effective radii, and has both a stellar and a dark matter component in mass. So with that, what we do is what we propose to call is like the stellar to total dynamical mass relation. And I want to stress that these 2 axes are completely independent. So this stellar mass cosmicity fitting, these total dynamical masses, as I just tell you about. And what we did is we color code again with the stellar population properties, ages and metallicities. And this can be easily seen by eye, but we also quantify with different techniques. Is that the scatter of the relation of fixed total mass also correlates with ages and metallicity. So galaxies that are more massive at fixed total mass tend to have older, are more metal-rich stellar population. This is quantified with a partial correlation analysis. For the sake of time, I won't explain this, but basically this red line indicates the maximal increase of the stellar population parameters. If it were vertical, it would mean that these stellar population properties only depend on stellar mass, but once the stellar mass dependence is taken into account, the idea is we also find a secondary dependence of ages and metallicities on total dynamical mass, which is what is shown here. And this is not only something that we see on the stellar population of the galaxies, but we also see when we probe another elements of the baryonic cycle. So this is stellar angular momentum, star formation rate, and Hubble type morphology. So basically what we are finding here is like these galaxies over here are more dispersion dominated, have lower star formation rates, earlier type morphologies, while these galaxies over here are more rotationally supported, have higher star formation rates and later type morphologies. And if you look at the direction in which this parameter change, it agrees as well with the stellar population properties. And this is quite interesting and this is also seen, for example, this is a work from William Baker and Roberto Maiolino, in which they study also gas phase metallicities. The axes are inverted, but basically, whilst they also find a primary dependence on of the gas phase metallicities on stellar mass, they are also finding a secondary dependence on total dynamical mass. Note that the dependence they found is weaker, but these total dynamical masses are only computed within 1 effective radii, and these are spiral galaxies only. Okay, but they find a trend that's in agreement with what we find. And this is, as I was saying, this is quite interesting because here you have a total dynamical mass relation, and here you have the stellar to halo mass relation with SDSS galaxies, and halo mass is coming from group and cluster catalogs. And when we can quantify these trends with the partial correlation analysis, which is shown here, you see how the maximal increase of the stellar population parameters is very similar in both cases. And in this way, total dynamical mass seems to mimic the behavior of the halo masses of the galaxies. Okay, so what do we think is happening here? So what's the physical origin of this trend? So while we investigate a little bit, for example, IMF variations, we don't think that is affecting these trends. We can discuss this later if you want. But what we're basically seeing is that these galaxies seem to have different evolutionary stages than these galaxies over here. So we find that these galaxies are older, are more metal-rich, are less rotationally supported, have lower star formation rates, and have earlier morphologies in comparison to these galaxies over here that seems to be younger, more metal-poor, have higher star formation rates, and later later type morphologies. So if we assume, or if we assume that total dynamical mass indeed behaves very similar to the halo masses of the galaxies, this is a well-known result in the field that is seen by different semi-analytical models and simulations, and is that the scatter of the stellar to halo mass relation correlates with the formation times of the halos, with galaxies that form in earlier forming halos being more massive than galaxies that form in later formed halos. And this is not only interesting because of the comparison between total dynamical masses and halo masses, but also because there's also been seen that when you, in hydro simulations, then if a halo forms earlier or later, it can affect the present-day properties of the galaxies. This is an experiment in which the galaxies were genetically modified, and what it turned out is that galaxies in earlier formed halos tend to have earlier type morphologies, lower star formation rates, lower gas fraction, and their black hole grow earlier, causing all these trends. So, basically what our interpretation is that the galaxy ages tightly map the formation times of the halos with the scatter of the total dynamical mass relation or stellar to halo mass relation, proving galaxies at different evolutionary stages. So here I give you with my conclusion. So our results seem to suggest that there is a connection between the baryonic properties of the galaxies and their host dark matter halos. So different galaxy properties depend on total dynamical mass, which is a dynamical tracer sensitive to the motions of the stars. And this total dynamical mass seems to mimic the behavior of the halo masses of the galaxies. So in our interpretation is that these trends might be driven by halo evolution, basically halo formation time. And we think that upcoming integral field spectroscopic surveys that extend to larger distances will be crucial to further test this scenario. With a halo assembly could be having a profound effect impacting the present-day properties of galaxies. So thank you very much.
Hi, I'm Kostav. So my question is, fantastic work, by the way. My question is, in the halo profile that you use to do the axisymmetric genes modeling, do you assume NFW, or do you do something like baryonification? Because at like 3R effective, those things can matter, right?
Yeah, I think it's, I didn't perform the dynamical modeling, so that's from the collaborators, but I think it's assumed that it's an NFW with a fixed concentration. Yes, I think. Yeah.
So I agree. This is awesome. This is Phil Mansfield. Sorry. Yeah. So I think a lot of the results here make a lot of sense. But I also have a question about the profile modeling. So this idea of a fixed concentration, we know that concentration correlates with halo age, which might mean that mass errors also correlate with halo age and therefore would scatter in there. Could you comment on what level of bias you would expect that to be?
Yeah, so like that's completely true, and I'm aware, but at the moment it's like these models are with fixed concentration, and it's like the degeneracies imposed in the fitting don't allow to do that, but yeah, we want to quantify this a bit more. Sorry, I'm not an expert on the dynamical modeling myself, so I cannot tell you more about it, but yeah, that's an important point, yes.
Hi, I'm Eliza Beveridge, and I have a question on the stellar population side. I was wondering how you measured the stellar masses. We were finding we did something very similar, but we used dynamical masses and compared them to stellar masses in the legacy sample, and we found that similar results with the iron trends, or metallicity trends, and also age trends, stellar population trends on that space. But we found that a lot of it could be explained by the degeneracy between age and metallicity and the stellar mass fitting. And I'm wondering what kind of metallicities maybe you assumed for the stellar mass fitting and how that was done, and if that could be
a thing that SED, again, like the SED fitting didn't perform myself. It was with growth, well, these stellar masses, you mean. this was SED fitting, so completely independent measurements with the photometry of the total dynamical masses. So in our first work here, this comes from the star population modeling with full spectral fitting. But this also agree with, like, we have the stellar masses is yeah, it's not a problem. Like, we can discuss it later, but it's not a problem. Yeah.
The next speaker could please come up. Well, Ramil S.
Yeah, sorry, I'm Ramil.
Yeah.
Yeah, really nice data. Just on the interpretation part, I think, sorry, this is more like a comment and a question, but the explanation for the halo formation time, I think, is really not very satisfying to me, and that's because essentially there's no reason to expect that earlier formed halos will necessarily host redder galaxies or anything like that. So yeah, there's a correlation there, but the reason for that correlation translating into the properties that you're actually seeing in the galaxies is actually extremely uncertain. And that's why, in fact, many simulations don't reproduce this trend. So one of the ones that does is SIMBA. So when we looked into this, the main driving factor was actually the black hole to stellar mass ratio. So the question then becomes, can you measure that somehow? Can you correlate this with black hole to stellar mass?
Yeah, I wanted to also point out, what I was mentioning also from the Eagle simulations, the earlier, it's a combination of the earlier assembly of the halo and the growth of the black hole. So what allowed these trends to happen was like an earlier formed halo allowed the black hole to grow earlier and also cause these trends. How to probe this observationally? Of course, at the moment it's quite challenging, so we thought that maybe to try to probe the concentration of the halos, as I was saying, with having rotation curves to a larger extent might be a way to probing that scenario, but of course, it's an interpretation, and there's not a direct connection between the two things. Yeah, we think that might be happening, but of course, there could be another explanations as well.